The final type of aggregate query I want to show you is how to calculate cumulative sums, also known as running totals. It's easy to calculate running sums in any type of reporting tool, but for a database, typically we need to calculate the running sum and store it so historically we can look back and know this was the running sum at a current point in time. A popular method of calculating cumulative sums is simply to use a correlated subquery. Let me show you how this works. This subquery refers to R, meaning the raw data, in the outer query. That's why it's a correlated subquery. And it will always sum all of the data where the sales date is less than or equal to the current sales date in the outer query. In real life, this would probably say where the sales date is equal to the beginning date and the current date to calculate that cumulative total. And execute, and I'll show you the result. Because it's doing this by date, and there are multiple rows for each date, it appears that the balance is 36, then 79, then 114, but that's because those two dates are being added together. But when you go beyond a larger data set, say 1,000 rows, the correlated subquery method does not scale well, because for every row it has to add up from the beginning to the current row. So the first row, it adds up the first row. Then the second row, 1 and 2. Third row, 1, 2, 3. Fourth row, 1, 2, 3, 4. By the time you get to 1,000 rows, it's adding up 1,000 rows to get the cumulative total for row 1,000. Then 1,001 rows, and then 1,002 rows. And it gets slower and slower as the data sets become large. Now at conferences, I've given talks called Kill the Cursor, and I'm no fan of cursors. In fact, I have a chapter in SQL Server 2005 Bible called Kill the Cursor. However, this is one case where the cursor outperforms the set-based solution. So to demonstrate this, I'm going to add a couple of columns. First one will be a balance and then an ID. The balance column is going to be where we store the balance, and the ID is so the cursor can step through each individual row. We'll also allow the cursor to start with some data in there. So I'm just going to use this simple correlated subquery method to populate a few of the beginning balances. 12 rows affected. That's pretty good. We'll look at cursors in more detail later, but basically the key part here is that for each row, that's what a cursor does, it steps through row by row. For each row, we're going to simply take the current balance and add to the current balance the new current amount. So for each row, the cursor is simply going to add the current row's value to the balance and then make that available to write back or to display whatever we want to do. In this case, we're going to go ahead and update and set the balance to the new current balance. So even if you're working on 1,000,000 rows, when you get to the 1,000,000th row, it just adds one row's value to the current balance and writes it. It scales very nicely as opposed to the correlated subquery. And let me execute this. Set up the variables. Set up the cursor, open the cursor, fetch the first one, continue to fetch until there's no more, close the cursor, clean up the memory. Zing, there's the result. I went ahead and added a print statement just so we can see it processing. Probably wouldn't do that in real life. And if we now look at the raw data, and I'll open this up, we did the first 12 rows to set the balance, and then after this, the cursor went through and added the balance for each row. And that's aggregate queries, the ability to take a data set, provide some summing, some aggregate functions, produce a single row, or to do a group by to segment that data set based upon different values, and then provide the summing aggregate functions for each one of those group by data sets. I showed you how to solve several common problems when working with aggregate queries. Then we topped it off with cool crosstab queries, even a dynamic crosstab query, and then how to work with high performance cumulative totals.